morning. In this lecture, we will see how to determine discrete Walsh coefficients. Now, let's take a quick problem. See, find the fourth element of the Walsh function having the order of 5 and length n is equal to 8. So, it can be represented as Walsh 5, 4, which means that, see, the total number of samples in the given time period is 8. So that is here length of the series, n is equal to 8. Let's see. What he is asking is order of 5, which means that k is equal to 5. And he is asking in the series having 8 elements, he wants to determine the order of 5, and the fourth element he wants to determine, which means that it is j is equal to 4. So this is the information which has been given for us. So when we do have this n is equal to 8, if we do represent it in the form of multiples of 2, then it can be written as, so which means it is 2 cubed. So this will become the value of r. So r is equal to, p is equal to, this will become p. So this will become p is equal to 3. Okay. So k is equal to 5 and j is equal to 4, right? So what we will do is nothing much. I'll check p is equal to 3, k is equal to 5 and j is equal to 4. So now these two are to be represented into binary of length 3. So k is equal to 5, which is in decimal. Now if I convert it into binary of 3 bits, so I'll get 101. So which means that this is k0, this is k1 and this is k2. Similarly, j also is to be converted into binary. So it is 100, this is j0, this is j1 and this is j2. Now let us apply the formula which we have gone through. This is the formula for determining the Walsh coefficients. Right. So now in my case this is 5 and this is 4. So Walsh 5, 4, where k is 5 and j is 4, right? So from 0 to 3, this value is 3, right? So minus 1 to the power of, now see here, this is the equation. So what I'll be getting here, p is 3, right? And this is, so what I'll be getting, if I substitute it, this is my value. So first of all, I'm supposed to substitute 0, next 1, next 2, next 3. So if I substitute 0, then I'll be getting this value. The next one and next two. See, this is not sigma, this is pi, which indicates every number is to be multiplied. And next I'll be substituting this k3, k2, k1, k0, whatever the numbers. If I don't have the number, I'll take it as 0. Okay. So if I substitute it, see what is the value which I'm getting here? It is minus 1. Right. So in the same way, we will be determining the different coefficients. We'll be determining the different coefficients of. Now let us suppose if you want to determine Walsh 6, 2. If I want to determine Walsh 6, 2, what will happen? It is by r is equal to 0 to 3. It is minus 1 to the power of k r plus k r minus 1. Sorry, 1 minute. I think I forgot the formula. This is kp minus r. This is p minus r minus 1 into jr, right? So in this case, now this will be varying from 0 to 3. So what is this one? Pi r is equal to 0 to 3. It is minus 1 to the power of k. It remains the same. This is 3 minus r plus k 2 minus r into jr, right? So in my case, 6 means it is k 1, 1, 0. So this is k0, k1 and k2. Now this is j, it is 2 means 0, 1, 0. So this is j0, this is j1, this is j2, right? So if I do it, so what I'll be getting here? So first of all, let me expand this one, minus 1 to the power of, first of all, I'll keep r is equal to 0. I'll get k3 plus k2 into J0 into minus 1 to the power of K2 plus K1 into J1 into minus 1 to the power of K1 plus K0 into J2. I don't have any K minus 1, I won't be getting, so that's why I'm stopping it here. K3 I don't have, but I'll take it as 0. So it is 0 plus K2 is 1. J0 is 0 into minus 1 to the power of K2 plus K1 is 1 plus 1. J1 is 1. Minus 1 to the power of this is 1 plus 0 and it is 0. So if I multiply it, I'll be getting minus 1 to the power of 0 into minus 1 to the power of 1. So minus 1 to the power of 2 into minus 1 to the power of 0. So this value is 1, this value is 1 and this value is 1. So I'll be getting 1. This is a discrete Walsh coefficient. Okay. So when I do have all the Walsh coefficients, so any periodic function f of t can be expanded over the interval. Okay, using this particular function. Just like you have seen representation using sinusoid functions. Same way in orthogonal square functions we can represent any periodic function, where this wk, which we call it as Walsh coefficient, this can be given as wk is equal to 1 by t integral t1 to t1 plus t f of t Walsh function, discrete Walsh coefficient. This is what we have done in the earlier slides. So this is the kth coefficient of the Walsh series and this is the kth order Walsh function. Okay. Now, having said this, I hope that in the next class we will be looking at how to determine these Walsh functions and also Walsh coefficients. So the conclusion of today's class is that any periodic function can be represented by a series of orthogonal square waves, which we call them as Walsh functions. And Walsh function is consequently useful where signals take the form of logical pulses, which are fundamentally rectangular in nature. So I hope that now you are able to determine the Walsh coefficients, and I hope that you are able to describe the properties of Walsh functions. So this is a problem. So now you are supposed to develop a matrix of 8 by 8 for 8 length Walsh function. You determine all the Walsh coefficients in that one, starting from Walsh 0, 0 to Walsh 7, 7. Okay. So with this, I hope that you can find additional information in this particular textbook, which I have already shared in the coursework. Thank you. We'll meet again in the class.